Hello everyone, my name is Muhammad Rasikh. My student ID is 101200049. I would like to take this opportunity to tell you about my research for seminar courses, which is being advised by Professor Muhtadi Intanditina. The topic of my research is secret sharing. Let's go first with this problem. Six scientists are working on a secret project. They wish to lock up the documents in a cabinet so that the cabinet can be opened if and only if three or more of the scientists are present. What is the smallest number of locks needed? And what is the smallest number of keys to the locks each scientist must carry? It is not hard to show that the minimal solution uses 15 locks and 10 keys per scientist. For any group of two scientists, there must be at least one lock they cannot open. Moreover, for any two different groups of two scientists, there must be two locks they cannot open, because if both cannot open the same lock, there is a group of three scientists among these two groups who will not be able to open the cabinet. So at least there are combination 2 of 6, which is equals to 15 locks are needed. Given that there are 15 locks and 4 scientists have a key to each of these locks, there must be 16 keys. Since 60 divided by 6 is equal to 10, each scientist should have 10 keys. These numbers are clearly impractical and they become exponentially worse when the number of scientists increases. So, my research aims to solve the problem that arises when the number of scientists increases. This research is based on Adi Shamir's 1979 paper titled How to Share Secret. In his paper, Shamir extends the problem to one where the secret is represented by some data k, such as the combination to a safe, and where it's acceptable to use non-mechanical solutions that manipulate this data. Shamir also demonstrates a method for breaking down data k into R pieces in such a way that k can be easily reconstructed from any row of these pieces, but having knowledge of row minus 1 pieces alone reveals no information about k whatsoever. This approach allows for the creation of robust key management strategies for a cryptographic system that can operate securely and dependably even in the worst scenario. So, what is secret sharing? Let's say a dealer holds a secret key, say a nuclear launch code that it wishes to share among some set of R users, P sub I and P sub R, by giving each user a share. Any raw user should be able to pool their shares and reconstruct the secret, but no coalition of fewer than raw users should get any information about K from their collective shares. We refer to such a sharing mechanism as a raw R threshold secret sharing scheme. So, in another definition, let rho and R be positive integers where rho is equal to R or less than. A rho R threshold scheme is a method of sharing a key K among a set of R participants denoted by P in such a way that any rho participants can compute the value of K, but no group of rho minus 1 participants can do so. So these are the steps. The D chooses are distinct non-zero elements of Z sub P denoted by X sub I, and then they gives the value of X I to P sub I. Then step 2, suppose D wants to share a key K, which is in Z sub P. They secretly chooses row minus 1 elements of Z sub P, which are denoted by A sub 1 until A sub row minus 1. And the next step is they compute the y sub I, which is equals to a evaluated in x sub I, where the function a is equal to k plus sigma a sub g x powered by g from 1 until rho minus 1 modulo p. And in the last step, they give the share y I to p sub I. So as an example, we will use 3, 6 threshold scheme in Z sub 13 to solve the problem mentioned earlier. See these following steps. They choose the sixth element of Z sub 13, and then suppose the key K equals to 7. They choose secretly two elements of Z sub 13, which is 3 and 7, and then the dealer will compute all of yi, and then this is the function 7 plus 3x plus 7x squared modulo 13. And then dealer will share all of y sub I to p sub I. And this is the shares. So if any three of the six scientists want to open the cabinet, they need to gather their partial keys for the dealer. Using the points that has been chosen, we can interpolate polynomials a using Lagrange interpolation formula. Hence, the value of k is obtained, that is k is equal to a evaluated in 0, which is equal to 7. In 2007, Tasse and Dean introduced the concept of interpolation bivariate Lagrange and stated the possibility of building a secret sharing scheme. The same year, Cameron Sani discovered a simple formula for multivariate Lagrange interpolation over field I. Then this is the scheme for using multivariate polynomials. Step 1, dealer D secretly choose a multivariate polynomial of degree n in Z sub p, where the combination n from n plus m is less than or equal to r, and its constant term is k. For simplicity, we will say the combination n from n plus m is denoted by rho. Then the next step is dealer will choose r distinct points on Z, namely this, such that every row points of the r points, its sample metric is non-singular. In the last step, they distribute share to p sub I secretly. The interesting aspect of my research is that its mathematical foundations are based on algebra and combinatorics. Furthermore, it finds practical application in cryptography, like the secure implementation of an encrypted backup system, bank swap unlocking code, and many more. Moreover, this research is open to development with numerous advancements in this area, such as secret sharing via skew polynomials, multi-secret sharing based on Hermite interpolation, and many more. That's all. Thank you very much. See you again.